Hello, my name is Stephen Palacios, and I would like to welcome everyone to my lesson about the introduction of Firefly synchronization using dynamical systems. For something to be classified as a dynamical system, it would have to be a system whose function is dependent on time, or in other words, changing over a set amount of time. There are two main types of dynamical systems: differential equations and iterated maps. Differential equations, which is something that should be familiar to those who have taken calculus, but just for a quick reminder, it is something that relates the physical quantities of typically two variables, such as x and y, and its derivative corresponds to its rate of change. Iterated maps is a little bit different, where it is used to model the dynamics in the population of a given species that is not dependent on time. Many engineers and scientists use dynamical systems to help understand the physical quantity of what is being studied, such as the vibration of a system and its relation to frequency and oscillation. There are many advantages to studying and viewing a topic with a dynamical analysis, such as to see how it changes over time, see if it sets to an equilibrium point or goes to zero, or it repels in a cycle either infinitely or until some outside force stops it. Here, we're going to see some examples that could be classified as a dynamical system. A wave harvester uses the repeated motion of the ocean waves to harvest kinetic energy from it. A common example is a swinging pendulum, where an object that has been moved from its initial position is let go from a certain height until it stops at its resting point. Finally, dynamical systems can even be applied to something as simple as fireflies, and I know what you are thinking. How does fireflies exactly work with something as complicated as this? To be more specific, it is the synchronization of the firefly's light that we are interested in applying this dynamical view. Around the 1970s, a person by the name of Frank E. Hansen studied this application of fireflies, and a mathematical model was created that relates the synchronization of the firefly's lights with that of a stimulus, in which in this case a flashlight was used. According to Hansen and his research, a firefly, specific to a species he was studying, responded to outside light sources with a delay of about 1 second, which equals the period of the natural spontaneous rhythm of flashing and includes about 800 milliseconds of central nervous delay. It was also noticed that fireflies can duplicate faster and slower rhythm of artificial light. Looking more into this study, the interval between the stimulus's light and the firefly's light of the next cycle approximates the firefly's normal free run period, which suggests that the stimulus resets the flash timing oscillator in the firefly's brain, thus providing a mechanism for synchronization. With the information that was previously stated, two mechanisms were concluded from the phase differences between the two systems: cycle-to-cycle phase shifting of a stable oscillator and changing the underlying period of a variable oscillator. At the end, by summarizing what was studied, naturally, fireflies that are out of sync will try to either speed up or slow down with one another to reach synchronization. In order for this dynamical analysis to commence, there were three attributes that were obtained: a general overview of the synchronization period, such as how long it takes them for their lights to sync up, the firefly's natural period, and the stimulus's artificial period, or in other words, how long it takes for each flicker to occur for both systems. In 1984, Ermintrout and Rinzel has created a model that relates the firefly's flashing rhythm to its response to the stimulus rhythm. Model 1 is the original equation developed, and Model 2 is the same equation but modified to give a different output, which we will talk about briefly later on in this lesson. Focusing on the first equation, lowercase theta represents the phase of the firefly's flashing rhythm. Theta dot signifies that it is dependent on time, so if this function were to equate to 0, this signifies the commencement of the firefly's flash. Of course, there are also other variables within the equation that help make this model more realistic to the situation, and they are as followed. A is the resetting strength of the firefly, which measures the firefly's ability to change its instantaneous frequency, or in other words, the ability to change when it starts to emit light. Lowercase omega represents the natural frequency of a firefly, and once again, as we could see here in the parentheses, theta equaling 0 represents the start of the firefly's flash, and the firefly going through a constant cycle at a frequency of lowercase omega, which can also be represented by equating the function theta dot to it. Similarly, capital theta is used to describe the stimulus's flashing rhythm, so this equating to 0 also means the commencement of its flash and its cycle with a frequency of capital omega, which can be represented by equating the function capital theta dot to it. One way to look at this is if capital theta is faster than lowercase theta, then the firefly would try to speed up, or theta dot would be greater than its natural frequency lowercase omega, because it is trying to catch up to the stimulus. Within the range of periods, the firefly and stimulus must be entrained, or in other words, the firefly's frequency matches with that of the stimulus. When something reaches entrainment, in this case, it basically means that the two systems flow with the same period. In order to see if they reach entrainment, the phase difference, represented as phi, can be achieved by subtracting the rhythm of the stimulus and firefly as seen in equation 3. So on a graph, this will allow us to see how much different in regards to position and each system's oscillation their max or min values are. In order to analyze the dynamics of the system as a whole, we could rearrange the phase difference to be dependent on time, and substituting what capital theta dot and theta dot was equal to as shown in the previous slide, it results in equation 4. To be more specific, equation 4 can be described as a non-uniform oscillator equation. So far, the systems that correspond to the stimulus's and firefly's rhythm of emitting light has been described as oscillators. But what does it mean for something to oscillate? And what does it mean for it to be described as non-uniform? Well, oscillations can be described as the frequent motion emitted by either a natural or unnatural system. Some examples are a machine vibrating by an outside force, such as the wave harvester that was shown at the beginning, or if you think about it, everything can be an example because everything has some form of natural frequency or vibration. There are two ways in which oscillations can be described, uniform or non-uniform. Pretty self-explanatory in the name, but if we were to attach equations to it, we could use a general lowercase omega to state that the oscillation flows with the same constant frequency throughout time. And for the non-uniform oscillation, we could use a general lowercase omega once again, but changing it by subtracting an amplitude to it with a sign function to signify that the flow is not the same throughout the system. Some traits of these two oscillations and a graphical point of view can be seen on this table. For uniform oscillations, it typically changes periodically by 2 pi after each full cycle. T can be used to describe the time period of the system completing one single cycle. Looking at the graph below, if we were to picture two systems, we could see that they oscillate at different frequencies, but come together at the intersecting points created by the axis. Finally, the amplitude determines the magnitude or height of the frequency on the graph, but since it is uniform, it remains constant or fixed. For non-uniform oscillations, the parameter A, which was attached to the trig function, introduces non-uniformity to the flow, and if we were to plug in values for each parameter, we could see how it takes place on the graph. So using the introduced equation associated with non-uniformity, making lowercase omega equal to 2 and A equal to 1 introduces non-uniformity as it starts higher from the axis and has no intersecting points as it takes a long time to pass the point near pi over 2. When A and lowercase omega equal to each other, non-uniformity has increased, oscillation has stopped, and a semi-stable point was created on the axis. Finally, when lowercase omega equals 2 and A equals 3, the intersecting point becomes 2 points, one being stable and the other unstable, in which the flow is attracted to the stable point as t goes to infinity. Now, the points created when the oscillation crosses the axis are actually called fixed points. Fixed points are defined as when the independent variable of the function, in most cases x, equates the function to 0, or in other words, its equilibrium position. Another way of simply understanding this is through the process as shown below. If we were to use the x dot equaling the function of x, plugging in 1 makes the function become 0, which means that that point is a fixed point. When I was explaining the uniform and non-uniform oscillations, I was referring to the intersecting points, now known as fixed points, as stable or unstable or semi-stable. In order to determine what type of fixed points we are dealing with, we could use the theorem as stated in the table, and we will refer to the points as x star. If the derivative of the function equates to something less than 0, it is stable. If the derivative of the function equates to something greater than 0, it is unstable. And if the function equals 0, then the test becomes inconclusive. If we were to look at an example of this, such as the function equaling to negative sine x, the corresponding derivative would be negative cosine x. Finding out what makes the equation 0 gives us the fixed points of 2 pi times n, 0, and pi plus 2 pi times n. Looking at the graph and using the fixed points to solve for the equilibrium solutions, the intersecting points are negative pi, 0, and pi. So when we plug them into the function, we notice that negative pi and pi is unstable because it is greater than 0, and 0 when plugged into the function is stable because it is less than 0. With the acquired information, we can get a better understanding of the flow of the oscillation. So looking at the graph again, when it approaches negative pi, the flow slows down and begins to repel from the point as it concaves outwards, then accelerates as 0 begins to attract the flow towards it, and once again repels away and slows down when it reaches pi. So before we could use what we just learned about oscillations and fixed points to analyze the synchronization of fireflies, the model must be non-dimensionalized. This basically means that the variables within the function that has a physical quantity, such as time or length, becomes unitless and easier to handle. So if we were to introduce tau to equate a times t, and mu to equate capital omega minus lowercase omega divided by a, we could start by rearranging what we stated by what is dependent on. So as we could see here, the change of tau over the change of time equals the change of phi over the change of tau times the change of tau over the change of time. With cancellation, we could achieve the change of phi over the change of tau times a. In doing so, and using the equation that was introduced before, we get capital omega minus lowercase omega minus a times sine of phi equals to a times mu minus a times sine of phi, where mu is actually the measure of the frequency difference between the two systems relative to the resetting strength of a. At the end, we get mu minus sine of phi as shown in equation 5, and this will be used as we move on with the analysis. Using the non-dimensionalized equation, we could view the parameter space, which is one-dimensional, to get a better understanding of how the oscillation of these systems behave with each other when attempting to reach entrainment. We start by achieving the fixed points, which are as followed: arcsine of mu plus 2 pi times n, and arcsine of negative mu plus 2 pi times n. We then continue with the analysis by taking the derivative of the function, which the result can be seen highlighted in yellow. For the first case, we could see the flow is towards a stable fixed point of 0, which corresponds to a value of -1. This means that when mu equals 0, the firefly and the stimulus are flashing simultaneously with a 0 phase difference, or in other words, the natural frequency of the firefly matches to the frequency of the stimulus. For the second case, we could see that fixed points come closer together, but the flow is still attracted to that of a fixed point greater than 0, which in this case is 0.866. This means that the stimulus frequency is greater than the firefly frequency, since mu now moves the curve upwards, causing an increase of velocity in the flow. Since the flow itself still approaches a stable fixed point, the firefly rhythm is still phase locked to the stimulus. This basically means that although they flash at the same frequency, the stimulus flashes at a quicker rate than the firefly, causing the firefly itself to want to catch up to it. But the phase of the stimulus will always be constantly greater. The final case, when mu is greater than 0, we could see that there is no fixed points. This means that the phase difference will keep increasing and not distinguish any uniform rate at which each system flashes. The phase difference beyond this case, if it were to be tested, will continue to show that both systems have failed to reach entrainment. Although we have observed the three cases previously mentioned, we can also consider mu equaling to 1 using the same setup from the previous slide. If this were the case, the graph pertains to one semi-stable fixed point at pi over 2. When a fixed point is semi-stable, the flow is attracted to one side and is repelled by the other. We could see that if we choose a value that is greater than pi over 2, it acquires a value of 0.866, which is unstable and causes the flow to move away from the point. And anything below pi over 2, which in this case acquired a value of negative 0.707, attracts the flow. This means that the difference between the stimulus frequency and the firefly frequency is equal to that of the amplitude of the resetting strength. It is also good to understand the range of mu in which both systems reach entrainment. Keeping the system within the range of omega minus a being less than or equal to omega and being less than or equal to omega plus a signifies the range of entrainment. This will also allow us to achieve a value for the resetting strength. In order to physically understand this, equation 6 is introduced, being sine of phi star equaling capital omega minus lowercase omega divided by a, with the conditions corresponding to the fixed points of phi dot, which is negative pi over 2 and pi over 2 to make the interval. With the range of entrainment, we could also acquire equation 7 to determine the time period for the phase difference that occurs between the two systems. As we could see here, the resetting strength A and the natural frequency of the firefly lowercase omega are presumed to be fixed points. Hence, achieving the drive frequency, which we could see here to be capital omega, in which a test can be completed. According to Hansen, if we were to apply this equation to the species of fireflies that is best known for synchronization, the equation shifts its frequency lowercase omega towards capital omega, resulting in a zero phase difference. Since we have covered the regular model that relates the rhythm of both the firefly and the stimulus, it is also good to view other possible forms that the model can take. Comparing it to the original equation proposed in the beginning, and as we could see here, an alternative model is when the function is multiplied by a variable f in which it turns the oscillation form from a sine wave to a triangle wave, which basically is a non-sinusoidal wave curve. So if we were to view this from a graphical point of view, the following intervals could be used as shown below. This is the graphical representation of the modified model. Once again, it is a linear wave curve. Why? Well, if we look at the intervals which I brought to this slide so we can have a better look, phi is in between negative pi over 2 and pi over 2. And if we were to plug in any values from that range into the function, the output is the same as the input. So generally speaking, plug in 0, we get 0. Plug in pi over 2, we get pi over 2. When the system passes pi over 2, we can now focus on the second condition. As we could see here, it decreases at a linear rate as what is being subtracted is pi from pi over 2 till it reaches 3 pi over 2. If we were to extend this outside the interval, it would repeat the motion as we could see here on the graph. Finally, as an overall view, as the flow reaches its max point, entrainment is reached, and when the flow decreases, entrainment is being lost. Finally, we can get the corresponding range of entrainment using the process as shown. Remembering that capital theta dot equals capital omega dot, theta dot equals the function of lowercase omega plus a times f times the difference of thetas, and the phase difference that was introduced before. Replacing the variables, we get phi dot equals to capital omega minus open parentheses lowercase omega plus a times f times the phase difference along with the two closing parentheses. We can then subtract everything within the parentheses to the other side. By dividing a times f to the other side, we get a function that is dependent on phi. Plugging it into the interval and multiplying a and adding lowercase omega to each side, we can then get a range of entrainment for the new model as shown in equation 8. We have reached the end of the lesson, and here are just some of the references that was used to put this lesson together. I hope you have enjoyed this lesson of viewing Firefly synchronization with dynamical systems. Once again, thank you very much for listening, and I hope you enjoy the rest of your day.